Good morning, everyone. I am a volunteer from the IAH Colombian chapter, and I want to welcome you to our fourth cycle of groundwater talks. We really appreciate your support to our chapter and join us for our volunteer activities. I would like to share with you our talks schedule for this week. So today we will present the Professor Carlos Molano talk. Tomorrow, if you want to join Luis Camilo Suescun, you need to register in the special link that is just in this presentation. So we will send those links today through the chat if you guys are interested to join Luis Camilo. On Wednesday, we will have Francesca Lotti talk. So will be through our YouTube channel. So you need to register. And on Thursday, we will have our talk with Mercat. So you need to register also to our webinar or to join us through the Zoom link that we have here. So we will also share that link with you guys through the chat. Also on Friday, Marco will present through our YouTube channel. So remember our rules and tips. So our talk will be less than 1 hour, and we will have a question session at the end of the presentation. So please leave your comments or your questions through our chat. In that way, we can read the questions and the Professor Carlos can answer the question. Now, I want to introduce to our speaker, Professor Carlos Molano. He graduated as a civil engineer from Los Andes University and holds a Master of Science in Engineering Hydrology from the Institute for Water Education in Delft. He is the Vice President of Latin American and Caribbean region for the IAH, and he is the founder of HydroGeoCol. He has more than 30 years of experience in groundwater engineering and environmental hydrogeology. Carlos is professor of groundwater flow and pollution in the Department of Civil, Environmental and Engineer at the Los Andes University in Bogota. His recently more significant contribution in the field of groundwater flow and pollution are his groundwater spreadsheets, solving difficult groundwater problems with sample spreadsheets accessible to all. So, Professor Carlos Molano, welcome to our talks.
Thank you very much, Paola. Good morning, everybody. So let's see, I have to switch on all the here and also to share my screen.
Yes.
Okay, here we are. So thank you for coming to this groundwater talk. And let's begin with my presentation. Okay, let's see. Okay, so today I want to share with you some of the application of SLUG tests and probably the more popular methods for analyze and SLUG tests that are the method of Hvorslev, the Cooper-Papadopulos Brideheff methods, and the Bouwer and Rice methods. So a few words about what I am doing now, just 2 slides. Well, this is Bogota, the Bogota plain, that flat area are quaternary deposits. And here we have some outcrop of Cretaceous rocks, mainly sandstone. So this is the recharge area of the main aquifer. Oh, the geology is very complex. We have here some faults, the Bogota faults. but I devote all my professional life between giving classes at the Universidad de los Andes that is located here near downtown, near the mountains, and consultancy service. Well, it's not shown here, but it's more to the left. And well, this is the Universidad Los Andes University campus. And this is the engineering building. So that's the place where I gave also classes and also some research. So here is the general outline of my talk. So I will also use a spreadsheet for the SLUG test. Some small introduction about what is a SLUG test, then the border vector for confined aquifer, then the Bouwer and Rice method for unconfined aquifers, and then the Cooper-Papadopulos for also for confined conditions. So let's begin with the SLUG test. Well, here is a confined aquifer. So we have here the aquifer, the water-bearing zone, so some clay or some impervious material here. And this is the well, the screen, the filter gravel pack, the well casing, and the annular seals. Well, very often we use in the bottom bentoniting pellets. Here some grout or some slurry of bentonite cements. And well, if the water enters through the screen, just goes to that static level, the piezometric level. And usually now we use a pressure transducer that we install in some part in the bottom or in some place between the water level and the screen. And the way is, the idea is to change in an instantaneous or near instantaneous way the water level in the well. So also I use an electric tape also to check and to calibrate the pressure transducer. Here is a solid device, call it SLUG, solid SLUG, or well, also in Latin America, call it solid Baylor. Also the SLUG test, well, here in Latin America, we call it pruebas de pulso and have other names, hydraulic conductivity test, piezometer test, bail down, although it has some other meaning. So we introduce in that device in the well. So water rises. Also, we can add water, but for environmental reasons, well, not always is good to use water. But in the past, we used also water to make the SLUG test. So it rises the water inside the well due to the water displacement of that device or the water displacement, but adding water. And we measure what's the behavior of the well in the well, but also in the aquifer. So it begins to drop down as a function of time, the water level inside the well. So that's the SLUG test. And well, eventually it goes to the static level. And then we can take out that SLUG. So, okay, so it drops the water. This is the most common practice here in Colombia. So SLUG test, so it drops the water and we measure, well, the recovery as a function of time. So that's the principles of of a SLUG test. It's the same for confined conditions. So usually, well, when the water do not intercept the screen, it's the same as the previous one. So you take out and you drop the water in the well and begins to recover as a function of time. When the screen intercepts the water walls, you have to take into account also the water, the porosity of the filter pack, because the water is not only coming from the aquifer, but also for the gravel pack. And usually for environmental reasons, sometimes we want to sample across the phreatic level, the water table. Okay, that is the same procedure to measure the recovery as a function of time. Some other, here we have some solid SLUG devices. This is from the Butler book, and you have here some kind of conic ends. And this is the device we use in Colombia. It's a solid SLUG, and it's threaded, so you can hear is here is the bottom end, a conic way, just to avoid the splash water. And so you can adapt the length, or you can shorten according to the field conditions. Here is the procedure in the field. Here is the SLUG. Here is already in the well. So this rope is to the SLUG. Here the electric tape, and this wire for the pressure transducer. So you have here 3 devices in the well. Well, sometimes we use a baler, also usually metallic baler for the SLUG, but mainly for bail down test. But the bail down test is almost always to measure the real thickness if there are free products floating on the water table. Okay, some other couple of slides. So here is the hollow stem auger. So we put here the gravel pack in the same way, the bentonite pellets through the annular space. Well, here is a hand auger, solid hand auger, and well, this for shallow wells, well, it's enough just put the bentonite pellets there. And also I want to show this slide that this is the push down technology, the GeoProf. And well, here we introduce a very small screen inside the casing. So you can push down as far as you are going down in the soil, so you can make a SLUG test in many points in depth. Well, there are a lot of references, but these are probably the books, at least are the books that I use. The book of Jim Butler. This is the first edition, the second edition. Even I don't have this new edition. It came out 1 or 2 years ago. And the Cruzman and the Reader pumping test book. This is the second edition with the assistance of Hanneke Verwey. Well, she works in the Columbia Geological Survey many, many years ago. Okay. So let's begin with the Hvorslev method. I don't want to go in so much detail. You can follow that in YouTube. But one way to derive the Hvorslev equation is from team equation for a pumping well in a confined aquifer under steady state conditions. So this is the well discharge, the drawdown, K times K as the hydraulic conductivity times the aquifer thickness. Here coincide with the screen length. This is the radius of influence here. And this is the effective well radius, W. So yeah, here is the well discharge. And well, in the SLUG test, the flow rate that comes from the aquifer is equal to the volume that accumulates inside the well, that is PR squares times the age. And for each that is the well discharge. So these two should be the same here. And that's the main issue of this approach. So here are some other algebra, and well, I changed the function, well, the water level, piezometric static level H0 is constant. So if you derive a constant is 0, and after some manipulation, you end up with this equation. So if you, this is what we call it the dimensionless drawdown, and, or that is the maximum drawdown. Here is 0, and this is the drawdown or the head that you measure as a function of time. So this is the equation. Oh, sorry. This is the equation, and this is just a straight line equation. Y you replace by a natural logarithm of E/E0, and this is the slope. So if you have a series of time dimensionless drawdown data, or normalized head, also is called this quantity. So you can have the slope that is M, and you know all the other parameters. So you can find the hydraulic conductivity. Well, this is, if you want to express just S over E0 independently, you have to, this is logarithm, so you have to take the exponent of that quantity. And for the radius of influence, there are mainly two approaches. One, to use the length of the screen, that's one. And also to use Butler showed that he got very good result with 200 times the effective well radius. Now, if the water level intercepts the screen, or you don't have this seal, well, you have to include the gravel pack, the flow through the gravel pack. So you have to replace that case in radius by this equation, which is a function of the porosity and of course of the well effective radius where is located the gravel pack. Hvorslev uses a time lag. Well, he used that time in his terminology, this T0. That is very easy because natural logarithm of 0.368 is -1. So divide or multiply by -1 is very easy. You can use the slope. So let's go to the first example. And well, in a moment, we are going to the spreadsheet. So this is a SLUG test here in Colombia. This is a typical SLUG test, well, a straight line, and add then some type of concave curve. So you fit that line to this part of the data, and you have here the S over S0, the dimensionless drawdown. And here are the equations. So this is I took from the previous slide. So you calculate the slope, but look, the slope is here in this strength line. So you just pick up from this equation, and at the end you find the hydraulic conductivity. Okay, so let's stop here for a moment. And this is, wow, I have here exercises. I give this as an assignment to my students. So, okay, this is example number 1. So, well, this is the static water level, just 1.1 meter before grade here. And the initial displacement, the effective well radius included the gravel pack, the well casing, and the length of the screen. So this is the time normalized head or normalized breakdown. So this is a semi-log, but the log scale is on the Y, not on the X. So we have here the time in seconds, and here the normalizer of dimensionless drawdown. And this is, these two columns are here.
Professor Carlos, sorry, but if you are showing an Excel file, we can just see your presentation. I mean.
Oh, sorry, I didn't know. How can I switch to my Excel file?
Do you have your Excel file on the same screen?
Yes.
Can you just minimize your presentation in order to see if we can see the.
Okay, sorry for that. Let's see if I can manage that. I didn't know, so let's. So you see there my presentation? Yes.
Yes.
Okay. Now you see my
presentation.
Again?
Presentation. Yes.
Well, I don't know. Well, that's well. How can I?
Did you minimize your presentation?
Yes. Yeah. You already. Let me see. Well, if the last slide I show you is this one.
Is this one? Yes. We just.
Okay. So
yes.
so I just put escape here.
Yes.
Yes. And if I minimize that,
nothing happened. I mean,
nothing happened.
Yes.
Oh no. Well, I will.
Okay, so maybe what about if you stop sharing and maybe to share again.
Okay, sorry for that, but okay. So let's share it again. Here is the example. So, oh, maybe it's because you can share just one file at the same time. So
yes, now, I think so.
Okay. Anyway,
yes,
we can
now
manage.
It's fine. Yes, okay, now it's perfect.
Thank you very much, Paula. Sorry for that. Okay. So, well, here, sorry. So again, we have here this is the same picture of the same graph that I got. So this is the spreadsheet or Excel, and the static water level from the surface, the initial displacement by the slug, the effective well radius, the casing radius, and the thickness of the formation that here for this specific case is equal to the length of the screen. Here in gray, if you can see, we have some information about the porosity of gravel pack. So in the case that water level intercepts the gravel pack, if you don't put any gravel, any bentonite, any seal in the annular space, you have to replace the radius of the casing by this effective radius. But this is not the case for this example. So again, so we have here in the x-axis the time. Here with the time, let's okay, yes, here is the time, and here the normalized head or dimensionless drawdown, as we call it. Here are the main formulas we use it. So this is the typical formula. This is the law, what is here in these brackets. So we can use, well, visually the first part. So probably up to this 4,800 seconds. So maybe less. Okay, 3,600. So we can also add, just to keep the original data. So we can add another data. So from our, well, you can also, the first data is equal 1, but is the maximum drawdown. So we can use this first part of 4,000, and also the normalized head up to 4,000. Okay. Okay. So, okay. So that's the data we are using now, because at the end you have this kind of typical concave curve of the time drawdown data. So you can make use of the Excel options. And well, this is not linear, of course. It's not logarithmic, because the logarithmic scale is on the y-axis. So it's exponential, or it is fit perfectly. You can also go, for example, the 2000, say yes, 2000 forward periods, just to see the straight line. Okay, so here it is. And you can display the equation on the screen here. And that's all what we need for now. You can, let's make more, only 14, yes. And to be precise, you can change here the format trend line level, and we can use scientific and more decimal places, 4 decimal places, okay? Yes, well, it's a long number. And you know, this number should be 1, but it is near 1, okay? So now, if we have the slope of that line, so we just put the number here, and it's minus 6.385. Well, that's enough approximation. And well, we have here the results. So let me, okay. So this is the log that I copy here for this Excel output. And this is the log. So here is the calculation of the hydraulic conductivity. And 1 included the radius of influence by the length of well screen. and here 200 times the effective well radius. So sometimes we use, you can use, are almost the same in the same order of magnitude, or you can take a mean value of both. Also, this is the time lag the whole Hvorslev used initially. So that's all the principles of the Hvorslev method. Have some other variation, but let's see another type of SLUG test data using the Hvorslev analysis. So let's go to another spreadsheet. I hope I can show you. So don't save. And okay, so I will share again. Let me put the second example here. And I will share the share screen. And here we are, share. Okay. So probably you are now seeing my Excel example. And it's exactly the same data. I took this data from the book of Butler. So he has these three columns. And these are the, well, he measured from the static level. So I put, you can use the water static level here as a datum, and the initial displacement and all the time head measures here. So this has like 2 or 3 kinds of behaviors. The first behavior here, the second behavior here, and the last behavior here. Well, Bouwer, well, in his papers, well, he told that this first part is because of a gravel pack drainage of behavior, but Butler finds that if you go from 0.15 to 0.25, you get some good results. So let's use that select data, the approximation recommended by Butler. All this is in his book. So we have to go to the 0.25. Well, it's near this. Let's go 25. Is this? Okay, so that's the Y. So this is not the. So we need the X. This. Okay, here. Oh no, for 25. Sorry for that. Okay. And then the Y values that is of column C. Okay. Well, yes. Well, let's put here. So it is just here from near 0.5 to 0.15. They are the same. Yes. Okay. And okay. It's just 4 points. Yes. And we made exactly the same procedure that we made in the previous example. So we add the trend line. I go fast because we already know. And we put the equation here on the chart. Okay. And yes. And we can also, okay, now that we are here, let's put the same scientific and 4 decimal places. Okay. Yes. And again to the trend line, and we can go here to the left up to, wow, we are almost here, so we can back near, well, if we are here, well, there's a lot of periods, so near the 90 periods backward. Okay. Well, more than 90, well, let's put 100. Okay, and you can also go to the other, the forward direction and other, I don't know. Well, no, so much. Well, it's a tricky thing. Okay, but we have here the slope, so you can see here in the screen, maybe we can have a larger number, 14. Okay, so just to put here the slope minus 8.3792 e to the minus 6. Okay, and you have here the hydraulic conductivity values that are almost the same values that got Butler in his book. So let's switch to another method. Let's go to the Bouwer and Rice method for unconfined conditions. So I will stop share and share again my other presentation. So let's go again. Okay. And let's share the screen with my presentation. So now you should see my PowerPoint, and let's go to the next screen. So here we are. That is the Bouwer and Rice method for unconfined aquifers. So the method of the Bouwer and Rice used is well, almost the same as I presented for the Hvorslev method. So this is the team equation, and they end up with the same equation. So in the original paper, they use just the natural logarithm of that drawdown, but it's the same, that you have the same slope. So some of the practical issues Bouwer and Rice method is that, well, they analyze the radius of influences that nobody knows, well, unless you have some piezometers near your well, but well, almost always you don't have piezometers, and so they view this as an empirical parameter and not as a actual radius of influence. So they determine that parameter using analog models and electric analog models, and they derive equations for unconfined conditions for this natural logarithm of this parameter, the theoretical radius of influences over the effective well radius. So for partially penetrating wells like this, they use this expression where A and B are empirical parameters, and the other parameters are information for the well setting. And for fully, well, here is, but this is for fully penetrating wells. They use this other expression for this C. So these are the Bouwer and Rice coefficients. And I will show you just in a minute in a spreadsheet. So this is the A parameter that depends of this expression. And this is the B, it has different scale, and the C. So this is I took this example from the book of Butler. So this is approximately the same vertical scale. So here is the thickness of the aquifer, of the saturated thickness, all the lengths in meters. Here is the length to the bottom of the screen length, the casing diameter, and the effective radius diameter. So I use this expression. Well, also Butler recommend for this kind, for the Bouwer and Rice, to use between the 20% and 30% of the normalized head. But let's go to the spreadsheet. So again, I stop share and let's see the spreadsheet I used. Oh, excuse me. And I will see the Bouwer and Rice data. Okay, so I will share again with you the Excel. So is this one? So now maybe you are now seeing my screen.
Yes, it's fine.
Okay, excellent. So the data I take from tables 6.1 and 6.2 from the book of Butler that are here. So this is the time head and the standardized head. And this I already showed. So is that the time normalized down here, and these well parameters are shown here. So again, the procedure is the same as in the Hvorslev. So this is the data. Okay, that is the time normalized down. So let's include, well, probably through this data, this is 199.6 second the time. So maybe we can include this data. So let's include the data as in the previous example, add, and the X values are from 0.1 to here. Okay. So, yeah, okay. Well, I don't know why well, it's easy to include this. Okay. Okay. Well, yes, that's so. Again, to use the trend line, Okay, so this is exponential. So you can see that. So we can again put the equation on chart. Here we are. And also to define more decimal here, this you can have a number and let's put 4 decimal places. Okay. Yes. And that's it. Okay, so here is the log. Also the same as in the is minus 0.0148. And whoa, it's minus. It's log. Yes, and it's a negative slope. Okay. So this is the hydraulic conductivity. That this is about the same value that Butler got. And well, so here the parameters A and B. You don't have I have here another spreadsheet that this is the reference when I use the polynomial approximation for these 3 values. And they, instead of using X, they use the log of X. And these are the groups. So I have already that functions. So you can just type here the A, the B. Well, for C also you have this other, but C is for completely penetrated wells. And this is this expression that is here below. And well, and finally, well, you have here also, well, I multiply that 86,400 seconds that have 1 day to be consistent in units. And well, that's the way we use the Bouwer and Rice method. Now, the last, well, time is flying, so the last is the Papadopulos Cooper pretty half example. And well, it's just one or two slides, but yes, I stop share. So I will go to the last, okay, well, I have to share it again. So screen share, and I share my presentation again. So now you should have seen my screen. And the British Papadopoulos, whoop. Okay. Well, actually it's the same procedure, but there is a very complicated integral parameter. So they call it the function, that is a function of beta and alpha. And beta is here. With this beta parameter, you can calculate the transmissivity, and the alpha parameter, you can calculate the storativity. So I use these 3 references, and we are going directly to the spreadsheet. So let me share with you that the spreadsheet. Okay. And to share again the screen. Okay, so now you should see my screen. So what is that method? So I include there directly the table from this reference. Well, also these values, you can get it in the reader and the Vostra book. And these are the function f. This is the beta parameter, and these are the alpha curves. So at the same scale, well, you put your SLUG test data, and I have here in the following. So this is just a table, yeah, and you have here all the groups. So here I make use of this scroll bar. So these are the parameters. It's almost the same. I uses the graphical cycle mode. The problem or the tricky thing is that this scroll bar is linearly arithmetically from 0 to 3000. Here you have a logarithmic scale, but with some transformation, well, here is the field data, the time drawdown data, and this is the normalized here. But I shift the time. This is the original time, so I shift the time to adjust that field SLUG test data to the closest curve. So also, this is a visual approximation. Okay, so I change the first point, and in the same way, all the points are linked to the first one. So up to you get, sometimes it's difficult to fit well. I reach near this curve, so you can quartz movement here, more or less to that curve. Yes, you can use that small arrow here. Yes, this last point do not fit well, but it fits with this 0.01 curve. Yes. So the transmissivity is very easy. It's just from this equation. Again, I multiply that 8,400 seconds. And the storage coefficient from this equation. So it is very easy. If you divide by the thickness of the formation of the aquifer, you got the hydraulic conductivity and the specific storativity. Well, sometimes it's difficult because it's very difficult. You have a perfect data as this one. And sometimes when you are in this area, it's difficult to fit exactly to that kind of curve. But that's another. And the advantage is that you can at least calculate or have some estimation of the storage coefficient. So well, I think it's all for now. I don't want to go to my presentation, and I really thanks all of you, especially to the International Association of Hydrogeologists, the Colombian chapter, the Colombian Association of Hydrogeologists, and to Camilo's school, Paola, and all his co-workers. Really great job for these pandemic times. So thank you very much for now. So I will stop share.
So thank you so much for your presentation, Professor. I am asking to our public if they want to ask questions, but for now we don't have questions from them. So I do have a question, and I saw in your CV that you made some spreadsheets that are for solving some problems in groundwater. So my question is, where the people can find those spreadsheets, or how the people can get those files?
Okay, in that case, I will share my last slide that is, let me share again if I can. So I can share my two last slides. And in the presentation that is, where is, oh, here, okay. So probably you will see now my screen and that, okay, are here. So that's my, well, I have to upload, and you can find this, I don't have upload yet. Also because, well, I use as an assignment to my students, so they got the answer, but now with this presentation, they already got the answers. It's in Spanish, but the spreadsheet you can find in this site is a Google site. And the tutorials, well, that is very easy. This is my name backwards, Carlos Molano. So you can find here, I have to also to replace some old tutorials. So that's my last two slides, and also now stop sharing. If anyone has some question, I will be happy to.
Thank you so much. So look, here we have a question. And Joanna Mesquita is asking, most of these models are proposed thinking of conventional aquifers held in sedimentary rocks. Which one of these methods do you recommend as an approach for aquifers on crystalline fractured rocks?
Yes, well, although the methods are developed mainly for, let's say, some homogeneous conventional aquifers, they use that also to detect the transmissivity in, for example, in a fracture. So they use it also sometimes, well, with some screen length of various meters, and apply the same, well, mainly the Hvorslev approximation for fractured rocks. We use it here in a pumping well in the sandstone aquifer, that is a fractured rock. And we just put a lot of water. Well, that well was drilled near the treatment plant. So we have all the water. So we just made some experiments a few years ago, and we got reasonable transmissivity results also.
We don't have more questions. So I really appreciate your time and your presentation and all your support and your work as a volunteer. And I think that is done for now. I want to share again my screen just in order to remember to our public that we have these talks scheduled for this week. And please remember to register for Luis Camilo Suescun talk and also for Mercat talk. So thank you so much for everything and have a good day.
Thank you. Thank you, everybody.